Thank you. I want to share a few thoughts with you, probably more than I should try to share with you, but some of the things that we've been doing. And I used a title here with the goal of trying to tell you that underneath everything that I'm going to talk about is simulation. And we've really, I think, seen a growth in the opportunity in simulation. And I'm going to talk more about that and have some ideas for you and some specific examples. But on there you'll see a couple of logos, or actually 3 logos. To the right is Purdue University. Its 150th anniversary is next year, just 1 year behind Edinburgh. By the way, the land-grant colleges in the United States were all founded in each state in the 1860s with the goal of creating universities that were about the agricultural and mechanical arts, or was the title of the act. The very top is the center that we founded and that I head, which is called the Composites Manufacturing Simulation Center. And to the lower left is ABAQUS, which is the Institute for Advanced Composites Manufacturing Innovation. It's a Department of Energy National Manufacturing Institute. There are, I think, 8 of those that have been founded. Maybe it's more. They seem to be being founded kind of regularly as we go forward. I run the simulation part of that. It's called Design, Modeling, and Simulation. Let's see if I can make this work. There we go. Just a little bit about the team that I have of both faculty and staff. This is a group of faculty and engineering staff that, does this thing work? Yeah. So we've attracted Jan Anders Monsen from EPFL in Switzerland to come and be my partner. I'm the executive director, he's the director, and then we each have grad students. There are faculty under us. Not under us, that they don't work for us per se, because we're not department heads, but they work with us, with the more senior faculty, and then a group of professional staff, some of whom are engineers, some of whom, for example, this is a visual communications person, so you can see why the quality of my graphs are pretty good. We actually have a first-rate person that does that. We live in something called the Indiana Manufacturing Institute. This building was built for us in our research park, and it is not a university building. So I live off campus, and that has some interesting possibilities, the most important of which is there is parking wherever we need it, right next to the building. So let's talk a little bit about simulation. What's happened in my lifetime in my field, in this field of composites, which I would like to say spans 50 years. It really started before 1968, but it began to pick up energy and momentum, if you will, in 1968. And I entered the picture actually in 1969. So next year is my 50th anniversary of working in my field. And so 150th of University of Purdue and 50th in my work. Question is, what happened during that time since I've been working in composites? Answer, a billion increase in computational power. A billion. Well, that's something you can work with. If something increases in power by a billion times, it means things have really changed, and that is really true. Simulation is now here, it's active, it's possible. I'm going to show you some things that were impossible when I started this work almost 30 years ago, and that we've done now. But put this in perspective. What am I talking about? What am I interested in composites? And the answer is carbon fibers. These things are about 5 microns in diameter. They're stronger than any known man-made material, and they're quite light because they're entirely carbon. They have densities about 1.8 grams per cubic centimeter. You can put that in perspective. It's quite a bit lighter than steel, and compared to the human hair, they're quite fine. Meaning, so do you think you could make an airplane out of this? Was the question in 1960 or thereabout when these were invented. Now, carbon fiber had been around for a long time, but it was invented in 1960, the one we work with today, polyacrylonitrile-based carbon fiber. Why? Because it's so strong. Nothing had this strength before. And it was invented here in the UK and in Japan, same time, 1960. Same fiber, interestingly enough. So why are we interested in these materials? Pretty simple. When you plot specific modulus versus specific strength, they sit right out here on the top of the curve. They give you better performance on almost anything you can get in a strength to weight ratio. And here's the typical spool of the material. Now, there's only one small problem. I got to figure out how to make an airplane out of something that's a thread. Well, man had this problem early on and learned how to make textiles from wool and cotton. It's the same problem. Well, not quite, is it? Almost. So we certainly use some of the same techniques, textile techniques, but we did learn how to do it. I mean, these are the things that have happened just since I've been watching. These are all carbon fiber based airplanes. They're all military. Here's one that you can't see with radar. This one you can't see with radar. Where's the, I think the F-35, that must be it there. It's either the F-35 or F-22. You can't see it and it goes quite fast. And so these were defense advances first, and this came out of the defense industry. It did not come out of the civilian sector in our country. And by the way, that's true in America. Much of our basic research is funded by defense. People like to think that that's not the case, but it is the case. Their budget in research is 2 or 3 times, maybe 10 times that of any of the others, except NIH is catching them, I think. Now, what's happened recently is we have a new wing program for the 777. It's called the 777X. The 787, that's all carbon fiber airplane, fuselage, wings, tail, everything. And on the new 777X, we have actually, we're going to have a wing which tilts up so that it can come into the airports and not get in the way of other airplanes. The wing is so long. This field, after defense, actually the first area was leisure products. And this is just one manifestation of that, but you all have seen golf shafts and tennis rackets and pole vault poles and all kinds of things that have been generated. There's some I'll say more about that in a moment. And then now we're working in cars. And the institute that I lead at Purdue is aimed at making lightweight cars from these same materials. And of course, the Germans did it first with the I-3, that is to say in a large production car. And look at the weight that you can save. I mean, 2 normal individuals can carry the body of a car. That's not true in today's steel-based systems. Got some work to go for sure, but we're getting there. So if you look at this, what's happened, and this is a kind of out-of-date thing, but just gets us to 2008, where about 50 million pounds of carbon fiber were consumed. Actually, this past year was 100 million pounds. So that growth is continuing. I think we will see 1 billion pounds of carbon fiber produced soon. By the way, you see the cost-volume ratio, the same trends on all materials. Now here's the interesting thing. If you're in aerospace and you look at how long it takes to develop a product, about 10 years to get a material into an airplane, and then you have almost another 20 years of use. So you've got some long-term issues. You can afford to invest lots of money. You got a lot of time to get the money back. Then if you go down to this lower-end consumer electronics, you're talking about sometime less than a year, sometimes months. Product is developed, delivered, and out of, sold, and all the money has to be recouped in that short time. So as you think about manufacturing and investments you can make, these are important consequences. We need to move aerospace from up here. We need to move it down to this level where we have in automobiles today, or even what we're seeing in sports is rapid turnaround of new ideas and new products that could be evaluated for all kinds of applications. So recently I met with Greg Heislip, who's the new CTO of Boeing, and you can read all the things that he said and that I stole from the newspaper, but at the very bottom he says, Byron, I'm really afraid we're going to be a company that is put out of business because somebody else figures out how to do this faster than we're doing it. So rate of manufacture of this process in composites. And you look at that and you say, well, if you're going to change the rate of manufacture, it isn't about moving people faster or moving products down the production line faster. It's about dealing with the manufacturing process itself, and I'll say more about that in a moment. But to put in perspective what that means, if I'm going to speed this process up, I have to speed up every one of these people that are in the supply chain. That's a daunting challenge. What's the one technology that I might be able to lean on to give me some help? Simulation. I'll come back to that in a moment as well. So, well, right now, in fact, I think the opportunity is that if we make simulation the language of innovation in manufacturing, then we can tie that supply chain together with the same language. It's the same as a language that we communicate in. We all know that we communicate in software languages like Fortran and others. Today, the language of manufacturing will be simulation of the phenomena, of the physical and chemical phenomena in place. And, excuse me, let me go back. I meant to get the pointer. Right now, the OEMs, Boeing and Airbus, they all have these big tools. They all have these big computer programs. They all have these big computers. But if you go down that supply chain very far, you don't have to go very far at all before you realize they just don't have it. It isn't like they have lesser quality. They don't have any. And so you've got the supply chain now supplying a company that they don't have the language to speak in. So that's got to change. And furthermore, the so-called digital thread of the future, where we design a part and we track that part digitally through its entire life. How can you do that if the supply chain doesn't have the language? So that's the theme of this work. And as I see it in the future, we have to have manufacturing-informed performance, meaning simulation teaches us how the part or system will manufacture before we make it. Because right now, the process is design it, perfect, make it imperfect, now try to figure out why it doesn't perform the way we designed it because of all the imperfections we put in manufacture. That's the current process. In fact, fracture mechanics came out of that whole idea. There's a defect in there. If we can find it, we can calculate its performance. Why do we have to have designed in or defects? We have to take that knowledge and understand the behavior, then we don't have to have defects. So this digital twin in manufacturing becomes a real issue, a real opportunity for your generation, frankly, students. This is what's coming. And we have created something called the Composites Virtual Factory Hub. I'll talk about that, and that's more about delivery of the software. And then I want to work through two examples of what we call workflow apps. Where did that come from? Well, I began to think about this and work with software companies, and what I realized was that what the engineer needs is something like a phone app, meaning that the solution that they're offered, the simulation solution, takes you where you want to go, not gives you something that looks like the front end of a jet aircraft where it's got thousands of buttons, you don't know which ones to touch. And that's the way current software is written, including Dassault Systems, my primary sponsor. They have something currently called the 3D Experience, which has got enormous capability. But it takes 3 guides to get you through the first steps to find out where anything is. But that's not what the world wants. The world wants a phone app. It wants an application. It wants, here's the problem I'm trying to solve, just work with this app, and it takes you all the way from beginning to end. And that's what we've begun to create. So I'm going to demonstrate prepreg platelet compression molding and additive manufacturing. The additive manufacturing, I have to tell you, is the work of my graduate student here, Eduardo Barrocio. So if you want real detail, I'll have to ask him for the detail because he did the work. So it reminds me of a story. It seems that there was a professor who was a distinguished professor and drove from site to site to give many lectures, and along the way his chauffeur said, you know, I've heard this talk so many times, I think I could give it. Of Well, the next university, they didn't know who was the speaker, didn't recognize him, so sure enough, the chauffeur gave the lecture. Well, at the end of the lecture, asked for questions, and one of the people in the audience asked a very detailed question, complex, clearly outside the ability of the chauffeur. So he was a bit of a quandary, and he stopped for a moment. He said, "Sir, that question is so simple, I'm going to ask my chauffeur to answer it." So there's my chauffeur. Okay, so the Composites Virtual Factory Hub, what is it? It's a delivery system. It takes commercial codes and it creates on the other side of them workflow apps, additive manufacturing, injection overmolding, high pressure RTM, compression molding. This is 4 of the methodologies we're developing. And to say that these guys are happy about that is kind of a mixed bag. They are, it's so interesting to talk to them because they all want to have this, they want to own it all. But none of them have the full capability. There will come a day, I suspect, I don't know how soon, maybe never, that Dassault Systems will have all these pieces, will own them, in which case they will have this capacity, but they don't have it today. And so they keep acquiring things. They've recently acquired a molecular modeling code. They call it BioVia, and so on. I won't spend more time on that. Here's just some of the things we intend to do. Additive, prepreg, 3D, preforms, autoclave, cost modeling, crash, overmolding, infusion molding. These are, I think, 8 of 12 that we're thinking about doing that we've started working on. Put that in perspective. But in the end, simulation codes don't go anywhere without people like this. These are 3 of my engineers. Rebecca Cutting is in Crash. Nate Sharp is Cure Kinetics. Mike Bogdanor runs the design studio. We have a design studio where a person can come in and say, I want this part designed. This group can design it. They all work for Mike. These are all, this is PhD, but she's close to PhD, not finished yet. And in that platform, what we're planning to have is a secure platform with cloud computing services, and we use Amazon Web Services for that purpose today. But we've built the hub based on a platform that was developed at Purdue called the Hub Zero platform. It was a National Science Foundation developed system. And here are the 4 apps that I was talking about. Additive manufacturing, which has as its base CATIA, Simplified 3D, E-Extreme, some of you know about these codes, and Simula. Both of these are Dassault Systems. And then injection overmolding, different companies and their codes, and so on. I showed this talk at the Dassault Systems major customer conference last week. And I'm still getting comments about the fact that I have Dassault Systems codes mixed in with others. How dare I have them touch one another? But the CEO and the Chief Technology Officer all agree that this is the present, if not the future. All right, let's take a walk down one app. This is compression molding prepreg platelet composites, meaning I take continuous fiber completely impregnated with thermoplastic polymer. It's continuous fiber, but I actually cut it into little pieces like this afterwards. I have, when I'm done with that, is I have little platelets that are about 0.1 millimeters thick, very thin, and they are any dimension I want, length to width. And I can then take those and mold a complex shape out of them that I cannot make with prepreg. I can't make these shapes with continuous fiber. It's impossible. We've tried. Every time we try, it's a big waste of time and effort. And the interesting thing about that is the orientation state these little guys take inside this molded part are directly a response to the geometry in which they're molding. So now you don't have the simplicity of designing a geometry based on an isotropic stress field. or material distribution, you have to design the part geometry for the molded mesostructure. I mean, this is real. It happens, and it's serious. Okay, so if you need to do that, this just shows you the different steps we need to go through. We need to understand the failure of it. We need to understand how the fibers orient during the molding process. We need to put all of that together in failure analysis and do tests and so on. This is the mold. Here's the part. You're going to hear more about the mold in a moment because we're going to 3D print the mold. That's the second app. So here's the first thing that we did was to develop this molding simulation. First of all, you need to know that this is, each of those colors is following the orientation state of a platelet. This is spherical particle dynamics formulation of the finite element method. It's the most advanced finite element modeling for what is actually solid mechanics. And why didn't we use fluid mechanics for this? It's an interesting question because it turns out the fluid mechanicians cannot solve this problem, in spite of the fact that they have been trying for 30 to 40 years. They can't do it. Why not? Well, because they are fluid mechanicians. They think everything flows like a fluid. It doesn't flow like a fluid. It flows like a highly anisotropic solid, actually, but just moves slowly, but it flows. And you need that kind of behavior and understanding. To do that, you have to redo how you think about materials and their deformation. So you have to build an anisotropic viscosity matrix or tensor, as the case may be. You can write that in this form for incompressibility, and then you express each of these terms in terms of the principal viscosities. This one is the elongational viscosity of the platelet system. It turns out these other two are pretty much the viscosity of the polymer with a small geometric change in it. But by the way, those differ by sometimes as much as a factor of a million. So that puts that in perspective. Once you've got that relationship, you can build a stress-strain relationship, stress-strain rate relationship, and you can use a conventional solid mechanics finite element model. We used ABAQUS in this case, and build with this methodology. We have a couple of different approaches, the implicit and explicit approaches to flow. And now you can take this data and map it into the orientation state. This is the orientation vector component in the vertical direction. If it's red, it means the fibers are pointing vertically. If it's blue, they're not pointing that way at all. They are probably lying in the plane. And we can map all three components of the orientation tensor throughout this part from this data, which is all predicted. Whoops, sorry, I went backwards. As usual, I was trying to point. This is predicted. This is now transformed into the material coordinate system, and we carry out now a solid mechanics kind of analysis to find failure behavior. But first, how good are those predictions? Are they good or not? And the answer is on the left is the molding simulation, and on the right is the CAT scan. So we've CAT scanned these and reassembled the CAT scan and compared the two. And when you look at that, you say, well, those sure look alike. Wrong, is it? He looks right. Well, let's do one experiment, which is to run around the circle a little and sweep out an area and then plot the components of the orientation tensor and see how our predictions and our plots of the actual measurements look. By the way, the flow is coming from here. It separates and then reconverges, reassembles here along what is called a knit line. Notice here that the fibers are all pointed now transverse to that, parallel to that line in that system. And so right here in that knit line area is an important, it should show a very high value of one orientation component, and that one should be parallel to this line, which is the X3 direction, and that's the peak. and then the one normal to the direction should take the minimum, and it does. And of course the outer plane should be relatively small. So this shows a very good relationship between prediction and observation in a fairly, I think, aggressive way. We've done many of these plots, and we keep surprising ourselves about how good this is. All right, now once you've got that internal mesostructure, you need to be able to predict strength. So let's make some tensile bars. Let's see if we can do, but we'll need a failure model. We build in the damage mechanics. This is continuum damage modeling. Does this even work for this class of materials? Very interesting question. Lots of work in this general area, and I wouldn't argue that we have absolutely the final answer here, but I think we have a good step in that direction. And here is, let's take a part, let's scan it, let's find out where the orientation state is. This is a measure of orientation with angle with this x1 direction. And so the fibers that are red, this region of red, they're mostly pointed in this direction, or they're blue, they're mostly 90 degrees to that direction in that area. And by the way, that affects the strength property and the behavioral characteristics. You cannot assume this material is homogeneous. It isn't, even at a scale that's of interest to us. Well, all materials ain't homogeneous at some scale, but this is a mesoscale that's reasonable. That's true. So here's a typical prediction. Not a this is the best, obviously. I wouldn't be showing it to you, but this is our experimental prediction on the right. You see the virtual sample, and you can see the intensity of deformation and damage here. And as this is the sample here showing damage. And if you look over here at the real sample, not only did it fail almost exactly in the same spot, but it failed along the same failure path. Meaning damage accumulation in this class of materials is a really good way to model them. Probably nothing better. Meaning also that you cannot use a representative volume element for these structure throughout the entire part. Okay, so you can take that then and go on to the more complex. This would be from the molding simulation what the deformations, the elastic deformation before failure. Failure in this gets more complex because you've got a lot of fastener pin interactions that I don't want to go into at this stage. Okay, let's stop and talk about the next app, which is the additive manufacturing app. And I call to your attention a company by the name of Thermwood, recently created in Indiana. They actually come out of the wood cutting industry. But this is a 3D printed piece, which we have a secondary milling step, which is a kind of a routing step, and then a coating step. And the height of this is more than 1 meter. So we're talking about printing things that are large. This is a large 3D printer. The ribbons that it's putting down are 3 centimeters probably, and maybe 5 to 10 millimeters thick, in that range. So why are we interested in this subject? Well, we want to print a tool to make this part. This is the part we made and just analyzed. This is the tool. Now this is Eduardo's work. This is a metal tool, actually, that we made this part in. So there's the part. But you can see that, no, this isn't the metal tool, Eduardo. This is the composite tool, isn't it? Anyway, it's in 2 halves. We put the little pieces of the platelet in there and then push it down, heat it up, push it down, melt it, and make this part with it. All right. So in 3D printing, the first thing you choose is the shape of the part. This is half of the mold that made that part. And can you print it anywhere close to this geometry? Well, first you've got to decide the geometry you want, put it in CATIA. Then you slice it, because 3D printing requires a slicing operation, if you will. Where do you put the layers? What orientation should they be? And here's our printing system in process. You can see the correspondence between this and this. They look a lot alike. A finished part that's not quite perfect, but so we have to go to a machining step, which is but it's really a surface finishing. And here's the finished part, which looks an awful lot like the original CAD geometries. That's the process that we go through. Now, can you model all those steps in such a way that you could design this part? Because interestingly enough, this shape and this shape are not the same. Wait a minute, you said you made it the same shape, you put it all in there. Well, it changed shape with residual stresses as it cooled to room temperature. And by the way, each layer was cooling at a different time. So you've got all of it, and you've got some creep characteristics going on. So can you capture all that? And by the way, if you could go back here and change this geometry such that this geometry would be the right one. Okay, so here's the flow chart. We do our CAD with the slicing. We do a bunch of material characterization, flow, microstructure, material behavior, polymer characteristics. We then understand heat flow, polymer crystallization, and residual stresses that are developing. And then we look at creep and shape change with that. And if you hook all those things together, you've got, in simulation, you can do the same thing, material flow and homogenization of properties. Now you hook that to process simulation, which it's got geometry in it, it's got slicing, it's got heat transfer and crystallization, it's got crystallization kinetics, stress, strength, and deformation. And then we have a performance simulation with the real microstructure that we put in there by design. And if we like what we get, we keep it. If we don't, we can reverse the process and change it. Here's a typical printing path being developed that you can see a simulation of this. And notice we don't make it solid. We have infill so that we can save material. And so that's in itself an engineering design problem. So there's the printed path. Here's the finite element simulation for the process, and the other side of which is we predict crystallization kinetics and residual stresses in the system, and out of that creep, obviously. In fact, here's creep. So here's the part deforming under temperature and putting in 1,000 psi internal pressure, as if you were molding something. The part itself creeps during that, and we want to find out how much and what is the deformed shape. Again, we want the proper shape of the molded part, not the mold. So the guided mold design, now if you have all those pieces, you can do, as we said before, you can iterate them in such a way that we produce the proper geometry initially. That's the whole point of that app. Okay, so there's the molded part, and there's the tool. This part was molded from a thermoset polymer. This is polyphenylene sulfide and 50% carbon fiber. This is epoxy with 60% carbon fiber. And this is made from platelets in this mold. So I've shown you two integrated workflow apps. I want to change slightly your attention now to talk about what's coming. What do we need to do if we're going to deliver this kind of working structure for the engineering profession? And I turn to the NASA Vision 2040. It wasn't that long ago we were thinking of 2020, but now we're not thinking about 2020 anymore. We're thinking about 2040 at near term, right? That's what's coming. So NASA has a very nice report, you might like to read it, that talks about multi-scale modeling and simulation, written as recently as 2018, and it has some elements in it that I think are worth repeating. First, what is this vision for this world that you're going to live in, you engineers that are coming along? It's a cyber, physical, social ecosystem. I like that point of view, because it is an ecosystem. This is all about products, developing products. It's all about, can you afford them? Can you empower the society with these things? But we need to accelerate this with concurrent design, development, deployment of materials and systems throughout the product life cycle of an affordable, producible aerospace application. Well, that's NASA, but I mean the car industry sees it the same way. So does everyone else. So what is their end state of this ecosystem? Accessible? All of us can get it? Could we get it on our own? Maybe. It's adaptive. Oh, new things are happening. You need to put them in it. But it's got to be changeable. It can't be so fixed that you can't change. Interoperable. Oh, these different codes need to talk to one another. Different companies need to have functionality that crosses their company. Robust, they shouldn't crash. Traceable, we need to find if we put some data in, we need, and a part fails on an airplane at a later date, we need to be able to trace it back all the way to that digital origin. And user-friendly. We need not to pull our hair out when we use this process. None of this is true today, by the way. So here's what I think are our future keys to success. How are we going to do this? We're going to have browser-based cloud computing. Forget this dedicated machine on your desktop that you own all the code in. Forget that. It's not going to be true. It's going to be adaptable, but we're going to have new apps incorporated as they evolve. Interoperable, we have multi-vendor integrated workflow apps. We're going to have this digital thread. Product life management is going to be routine. They're going to be user-friendly, so the tools are focused on the specific applications. And then we put that in the supply chain, and we, by the way, have to keep the learning process going. How do you do that? I think we in academia have this tough problem that we don't teach the content as much as we did before. We now have to teach understanding. Harder to do, I might add. And I think there's things coming like this pervasive tool learning and the virtual laboratory that will help with that. But there are some challenges. Number one, the tools keep changing. That fights against standardization. Number two, a lot of this happens with small businesses. How do you, these big, how does this all work economically? And this agility of receiving these new acquisitions, these new vehicles. I mean, suppose a guy has a great idea and starts building a code. How does a big company absorb that? How does it work? Don't know the answers to that fully. This digital thread, I think, is challenged by the fact that these different codes don't speak to one another today. How in the world can you hand off? It's almost like handing off evidence in a legal case. How do you hand off from one place to another and assure that it was handed properly and didn't change in the process of being handed off? And so this digital thread, I think, is going to be called the digital pipeline, but we have to have fidelity. We have to capture all of manufacturing. We have to do the variability in meso microstructure, and additive manufacturing can put great demands on that, in my opinion, what's coming. So my summary is, I leave you with this thought. Simulation is the language of manufacturing innovation. This ecosystem of 2040 involves the digital thread, this end-to-end simulations and apps, and here are all the things we need. The last one I would add is it's going to be pervasive. And pervasiveness is coming so that it is everywhere, and we have to deal with it in a very effective way. I want to thank my sponsors. The Boeing Company has been a strong supporter of us for a lot of years, and this institute that's providing a lot of the funding in these two projects, the compression molding projects, Boeing funded, and the manufacturing was the institute funded. So thank you very much for your attention. I'll be glad to answer any questions.